problem. There it is. That circuit doesn't look too bad. We're going to work through this one together. And then as soon as we finish this circuit, I'm going to give you one to work and give you like 15 minutes to work on it. And then I'm going to talk a little bit more. Okay? Sound good? So if you pay attention now, you're going to understand how to do the circuit I'm going to give you, and life is going to be good, and you're going to have one of your homework problems done. And that's going to be fantastic. And that's going to be way better than the way I'm treating this other class tomorrow. Yeah. So anyway, let's work this problem. Notice there's not much that's being asked here. Find the energy lost, and this isn't going to make any sense to us right now, but I'll explain, due to Joule heating in resistor R2 in 15 minutes. Let me tell you exactly what that's talking about. Just first of all, ignore this word Joule. You don't need to know anything about that. Here's what I will tell you that it's asking for. It's essentially asking for just the energy lost, okay? As current goes through a resistor, it gets a little warm, just like with a light bulb, right? You pass current through it, it lights up, it gives off light and heat because it gets hot, and there's some energy that's lost there. So, first of all, we learned about this equation. Remember, power is equal to I squared times R. Okay, we talked about that very briefly. And also, power is equal to energy divided by time. Energy divided by time. Let me move that down so you can actually see it. I always forget that things are cut off a little bit in here. Okay, so what we're going to do is find that energy is equal to power times time, which is I squared times R times time. But we only want to do this for resistor 2. Resistor 2, the one right there in the middle. Which means that, well, they gave us a time, 15 minutes. We know the value of resistor 2. It's given up here as 3.5 kiloohms. The thing I'm going to need to find is how much current is passing through that resistor. Okay? So I need I2 in order to be able to solve this. Okay? I need to find the current that's passing through resistor 2. And we're going to go through a whole sequence of events to find that. All right? So the first thing I need to do to be able to sort this out is to just simplify the circuit all the way down to one resistor, one equivalent resistor, one resistor to rule them all, if you want to think about it that way, okay? So we need to simplify the circuit by just finding parts that are in series and parallel and then slowly making the circuit all the way down to one resistor. So take a look at these 4 resistors and tell me a relationship between just 2 of them that you are 100% sure is true. Tell me 2 resistors that are either in series or parallel. Yeah?
R3 and R4.
I would agree with that. R3 and R4, those 2 on the right, are in series. If you just imagine current arriving, say, at this location, I don't know how much, I don't know where it's coming from, none of that really matters. It's going to pass through resistor 3, and then it has no choice but to pass through resistor 4. Okay? So let's just start with simply that and say that R3 and R4 are in series. R3 and R4 are in series. To help ourselves out, I'm going to make a little note just underneath this. Remember that if they're in series, they have the same current passing through them. So whatever current is passing through resistor 3 is going to be the same as the current that's passing through resistor 4. And once I put them together, I'm going to call that the combination of 3 and 4. And that combination will have the same shared current as well. So I'm going to call that I34. R3 and R4 are in series, so they share the same current. Okay? So let's do the equivalent resistance part for just this. We could say that R34 is equal to R3 plus R4. In series, it's as easy as that. We just add them together. So let's look at the values that they gave us. Notice everything is in kiloohms, so R3 is actually 2,000 ohms. and R4 is 1200 ohms. So let's write those out. We've got 2000 plus 1200. So nothing too difficult there. R34 is 3200 ohms. Okay, so that's the first step. Good so far? Not too bad? Okay. I'm going to redraw the circuit each step of the way so we can kind of see what's happening. It doesn't have to be neat. I just need a little sketch of where we stand with things. Okay. So at this point, we could draw something like this. We've got our battery down here. We've got an R1 there and R2 here. And now we've combined those last three resistors, and we're calling that R34. Okay? That's the circuit as it currently stands. Now, look at the new circuit and find another relationship between a couple resistors that you are sure exist. Two of them that are in series or two of them that are in parallel. What's that? They're all in parallel? They're not all in parallel. I would agree with that. Yeah, there we go. Okay, so let's trace this around just a little bit. Notice this point that's actually marked, that's a dividing point for the current. Okay, so the current can go around to the right side, or it can go straight through resistor 2, and that all comes back together at this point. Okay, at that point we've finished the relationship that's happening here, and it had nothing to do with R1. So we can say that R2 is in parallel with this other branch, which we combined as R34. Okay? Soak that in. Do you feel okay about it?
Wait, can you explain the dividing thing again?
Okay. So the current starts here, gets to this point, and then has options. It can travel along this path, or it can travel along that path. Both of those paths reconvene right there. Okay? So because R2 and R34 share this splitting point on one side and share the coming back together point on the other side, we can say that they're in parallel with each other. Okay? So let's go ahead and write that down. I'm going to go over here to the side. Ooh, where do I want to do this? Let's go ahead and do this right here. So we're going to say that R2 and R34 are in parallel. And what do they have in common if they're in parallel? Potential, voltage. So I'm going to write down as a note to myself for later that V2 is equal to V34. And once I put them together and combine them, well, they're still going to have the same points on both sides. So I'm going to say that that's also equal to V234, the combination of 2 and 3,4. Okay? And then we're going to find the equivalent resistance for this combination. So I can say that 1 over R234, which is the combination of all three of those now, is equal to 1 over R2. Did you hear that? Anybody? No? You didn't hear it? You know, the thing about the stuff. No? I'll say it again, yeah. So we've got 1 over R234 is equal to, prepare yourself, 1 over R2. See, it's just there. It's subtle. Yeah, the D2 always follows the R2. You can't help but, like, it just, even if it's not verbally said, like, just mentally. I know some of you are like freaking out, like, there's ghosts. He's hearing things. What's happening? It's Halloween a day early. What's going on? No, there's just always a D2 that follows R2. Like, it's just, like, I can't not hear it every single time. So 1 over R2, see? It's just kind of, ooh, yeah. Plus 1 over R34, okay? And we'll plug our numbers in. We know R2. I should just train classes that every time I say R2, they're all like, D2! That'd be kind of fantastic. Scary for everyone, but it'd be kind of fantastic. So 1 over that, plus 1 over the thing we just found from just above, and then take the reciprocal after we add them. Somebody tell me what you get for R234. 1671. Let me see if that number is what I have here somewhere. 1671. That works for me. 1671 ohms. And then I'm going to redraw the circuit again. We have now combined these parallel branches on the right, and we've called that 234. So let's redraw this again with R1 here, and then we've got our battery there, and now over on this side we've got R234. And at this point it becomes pretty apparent what's left, right? Question?
So when you, so 3, 4, you obviously just added them together.
Yep.
But then did you like subtract? How did you get 2, 3, 4 again?
234 is from this equation. So 1 over R2, which is 3,500, plus 1 over R34, which is 3,200. Take the reciprocals, add them, take the reciprocal.
But you take the reciprocal of that?
At the end, because 1 over R234 is whatever this is.
Yeah, and then you're trying to find.
Trying to find just what's in that denominator.
Okay.
Okay? So be careful. If you're a little worried, that like maybe you just double check and make sure you get these same numbers if you're worried about the calculation. Okay? What's the relationship now? Once we like step through and redraw these, it becomes a little more apparent, sort of like what's happening, as opposed to trying to look at everything at the same time. The things that are left are in series with each other. So I can say that R1 and R234 are in series, which means that they're going to have the same current passing through all of them. So I1 is going to be equal to the current through I234. And really, like everything here is getting all of the current, right? Whatever leaves the battery is going to go through 234 and then go through number 1 and come back around. It can't go anywhere else. So really, I could just call this, well, 2 different things. I1234, if you really wanted to just kind of continue this notation. Now everything is in there. Or I could say that it is the total current. Okay, the total current is what's passing through each of these. This problem can be done sort of faster. I'm trying to be really explicit with it by going through each step. After you get a little practice, you might find like maybe you don't need to write all of these things down, but I think it'll help as you go back through and try to work problems on your own and do the homework, etc. Okay? So here at the end, let's add these things together. So at this point, we're finding R1234, which is really the total resistance. It's the equivalent resistance for the entire circuit. And it's going to be just the sum of R1 and R234. And looking back at our numbers, R1 is 570, R234 is what we just found. So you should get 2241, I think. That is the equivalent resistance for the entire circuit. I could take all 4 of those resistors out, just put the 1 there, same circuit. There is no difference between the 2. Although you're thinking, why are we doing all this? I thought we were trying to find this one current through this one resistor. We're getting there, okay? To actually get there, this is the first step you're really gonna have to do every time. We need to find how much current there is like in the circuit as a whole before I can find out how much is going through one little part of it, okay? So once we have that, let me just switch colors here so I can indicate that we're gonna go use this other little space over here next. So I'm gonna take this, right here, okay? REQ, and I'm gonna use this in an equation for the entire circuit, which is Ohm's law, and everything here is about the total. So we're talking about the circuit as a whole, the total voltage, the total current, the total resistance, okay? And I can solve that for the total current, which is going to be V total over REQ. And they told us V total is up here at the top. They use slightly different terminology, so let me rewrite that. Is 15, and REQ we just found to be 2241. Divide those, and what do you get? Hmm? 0067? Okay. 0067. An idea. Maybe all the answers on my final exam tomorrow night should just be 666. That'd be kind of fantastic. Or it's like hidden in the answer somewhere. And then people will be like, wait a minute. They get to the last problem and there's no 666 in their answer. They'll be studying away. Like there has to be a way to find it in there somewhere. That could be kind of dark. It's a thought. I think it's too late now. And I don't think there's anything I can do about it at this point. What's the unit here? Amps, 0.0067. That's the total amount of current that comes out of the side of the battery and begins to follow the paths that are laid out before it, okay? So starting right here, we have I total. And it's heading into that first splitting point where some is going to go through R2. Yeah, there it was again. And some of it goes through that other branch. We want to find out how much goes through that R2 branch, okay? So let's see if we can sort this out. And to do that, I'm going to add another slide, I think. Hey, look, I already had another slide here to do it. Why have I been trying to cram everything into such a small space? Look at that. I thought out things in advance. Weird. What's wrong with me? I don't understand. So let's see. We just discovered that the total current is 0.0067 amps. Go back and look at that previous slide and you'll see that we made ourselves a little note that tells us some other things that that current is equal to. That comes in handy, okay? I'm trying to work my way back to finding the current through number 2, okay? That's gonna help us out at some point, okay? So we know that I total, the number we just found, is also equal to this current through the combination 2, 3, 4. This combination resistor, all right? So let's put that in there as well. This is equal to I, 2, 3, 4. And then I'm going to start repeatedly using Ohm's law for different little parts of the circuit. So I can say that the potential difference across 2, 3, 4 is equal to I, 2, 3, 4 times R, 2, 3, 4. We're just applying Ohm's law, not to the whole circuit now, but to one little combination part of the circuit. In other words, looking back at our circuit, we're just applying Ohm's law to that resistor, okay? It's going to use whatever the potential difference is, the drop in potential as the current flows through that resistor, and it's also going to use how much current is flowing through there, okay? So if we go through this, what do I not know? I know this value for R, and I know this value for I, which means I can find V234. It's equal to 0.0067 times, what was R234? It's back there somewhere. 1671? Is that what we had? So V234 is what? 0.0067 times 1671. Go. 11 point, let's just say 2 volts. Question? 11.2 volts. So go back. Let me look at the circuit and figure out what we've discovered here. Basically, we know how much current is passing through that resistor, okay? Whatever current is passing through 2, 3, 4. And we found the voltage drop as we go from one side of that resistor to the other, okay? 11.2 out of the total of 15 volts is getting used up, which means that even though we don't need to know this, right? If it goes down 11.2 here, it's got to go down the rest of the way as it goes across that other resistor. How much voltage is left? It was up at 15, it went down 11.2, It's got to go the rest of the way. It sounds like there's 3.8 that will drop for this other resistor as it comes back around to the beginning. Okay? All of these little parts of the circuit, like you should be able to come at it different directions and all the numbers sort of add up and make sense no matter which part of the circuit you look at. Okay? So what do we know that V234 is also equal to? Let's go back to this. Notice V234 is the same as V34 is the same as V2. Now we've got something that's just about the resistor that I'm worried about. Okay? So we can say that this 11.2 volts is the same as the potential drop across resistor 2 all by itself. And if you go back and look at that circuit in its entirety, that should sort of make sense. Okay? 11.2 is the potential difference between here and here across just resistor 2, or across the combination of 3 and 4, or across the combination of all 3 of them. That's the potential difference between those 2 red dots. So once I have that, and now we're getting close, I can use Ohm's law once again and say V2 is equal to I2 times R2. And we can find the current through resistor 2. So I2 is equal to V2 over R2. That's 11.2 over R2, which is 3,500. And I've got 0.0032 amps for that one. Okay. Now, before I go any further, I still want to kind of point out how some of these circuit parts are fitting together. Remember we said the total amount of current here was 0.0067. We just found out that some of that went this direction, right? 0.0032 goes through resistor 2. But some of it keeps going straight, right? How much of it keeps going straight? Yeah, 0.0035, right? The amount that's there has to stay the same. So the total amount of current stays the same. Some of it goes off one direction, some of it goes the other direction, and then they add back together over here. And once I get to this point, it's back to 0.0067, and that's how much would go through resistor 1, okay? Literally see it like these streams of current. There's a certain amount. I can't get any more and I can't lose any. I should be able to track where all of it goes through the different branches, okay? Yeah?
Is the resistor basically like kind of slow calories or like?
What does it do? You can think of it as sort of consuming a little bit of energy through collisions.
So it is using up some.
It's not using current. It's
losing some.
It's not losing current because once I get to the other side of resistor, same amount's still there. It flows through. It maybe just has some difficulty getting through.
So it just takes more time to get through, right?
I don't even know if time's the right term. Think back to the waterfalls. Okay, if you imagine a waterfall as just simply a drop from one level to another, like as that water falls, you can imagine it like is going at one velocity and it like speeds up, and like I could put an object in there and it could turn it and do work and things. That's essentially what all the electrical devices are. There's something the current can flow through, and as it flows through, it can make things happen. It's that opposition because of collisions at the microscopic level that essentially is exerting forces on things and physically making things occur. Okay. Where does this leave us? Where are we in this problem? Let's go back. What are we looking for? This thing up here. Energy is equal to I squared times R times T. And that's going to tell me how much energy gets used up by resistor 2 specifically over a period of 15 minutes. Okay? So at this point, we can say that energy is equal to I squared R times T. And we're specifically looking at the second resistor. So I'm going to put a subscript 2 on everything. We now know this is 0.0032. We're going to square that. Resistor 2 is 3,500. And to be consistent with the units, I can't use minutes. That's not a proper SI unit. Instead, I need that in seconds. So 15 minutes times 60 seconds, we'll get that into seconds. So we're going to write that as 15 times 60. And if you put all that together, you should get about 32 joules of energy. 32 joules of energy. That's a lot of stuff. You will find as we progress through chapter 28, there are essentially 3 main problem types, and you'll see that reflected in your homework as well. There's series and parallel resistor circuits, being able to sort of analyze every little part of it, okay? We're going to have like a little bit more complicated, I'm sorry to say that, version of this that are called Kirchhoff's laws. We're going to use some of that. I'll have to teach you that next time. And then there's circuits that have both resistors and capacitors in it. There's like 3 main problem types, okay? So what we're going to do, it is 4:24. I'm going to take just the next few minutes till about 4:30 to go back and kind of see what's left in the chapter. 2 things I want to talk about. First of all, a new type of circuit. And it turns out that you just basically have some set equations for these. If you can kind of understand the basic idea of how they work, you can quickly get to answers. So I'm going to describe how they work, describe the equations, and we'll do an example, and then we'll have the other thing about lab-related material. So notice, this is a new circuit called the RC circuit. It is exactly what you might expect. It's a circuit that has both a resistor and a capacitor. It's a combo circuit, a little bit of both. So it could be multiple resistors, it could be multiple capacitors, but it has at least 1 resistor and 1 capacitor in it. So you will notice here in this first circuit on the left, we've got a voltage source, we've got 1 resistor, we've got 1 capacitor, and currently there's a switch up there that's open, so nothing is happening. The circuit is just sitting there. We're going to say at the starting time t equals 0, we're going to close the switch. Okay, and you'll notice this just agrees with what they've said here. At earlier times, the switch is open, nothing is happening. Oh, that's not how you spell nothing. And then after t equals 0, the switch is closed, and you'll see that current is flowing toward the capacitor, and we would say here that the capacitor is charging. And over here at the beginning, the capacitor is uncharged. And you may remember we talked like in some detail about sort of how a capacitor charges, and we talked about like, yay, they have a place to go, and the charges start to run that direction. And as it begins to fill up, it's like, there's more like charges over there. I don't necessarily want to go. And it gets more and more difficult to fit more charges on because of the repulsion. And at some point, the capacitor's full, the current stops, and it's just done. And then I can disconnect it and go use it to power something else. What we're doing at this point is sort of zooming in on that period of time where charges are running over to the capacitor, filling it up. Previously, we just said it happens, now it's charged. We're now going to look at that charging process. That's what's happening here. So we go from a case of an uncharged capacitor to a case where time is going forward and we're beginning to fill up the capacitor. So based on the description we had before, maybe we start with lots of charges going. They're like, yay, so that's a lot of current. But then as time goes by, less and less charge goes that way. The current starts to drop until the capacitor's full, and then there's no current at all. So it's like I have a temporary circuit. Something happens for a little period of time, and then it's just sitting there waiting for me to disconnect the capacitor and go do something else, all right? So what's going to happen in these circuits is that the potential V the resistance R and the capacitance C are going to be constant values. They are fixed things in the circuit. The battery has a certain potential. The resistor and capacitor are physical things that have a value. But some other things are going to be changing. So we could say that the current in the circuit, the charge on the capacitor, and the voltage across the capacitor will be changing with time. As time goes by, we're going to have different values for all those. Previously, we just looked at Q and V sort of at the end. It's completely charged. What's the potential difference? How much charge does it hold? Now we're looking at all of the times in between when it's at different states of charging. It's partially charged. So we're going to have three things in the circuit that are constant and three things that are varying with time. They are functions of time. So we can no longer just say like how much charge is on the capacitor without asking when. At what time do I have a certain amount of charge on the capacitor? Okay, because it's always going to be a different amount. In this type of circuit, we just can't say what is the current. You have to say when do I, at this particular time, what is the current? Okay, because everything is going to be changing. This is what that looks like graphically. So here on the left, we have specifically the charge that's on the capacitor as a function of time. You can see that we start out with no charge, and then that charge rapidly builds, but then sort of begins to tail off as it gets closer and closer toward full, okay? So it starts out quickly and then begins to reach some maximum value where I have the maximum amount of charge on the circuit. So this dotted line represents Q equals C times V. This is the maximum charge on that capacitor. So over time, it's approaching that maximum. On the right-hand side, we have the current that's flowing through the circuit. And you can see we start at an absolute maximum value. As soon as I close the switch, it's like current, yay! But then very quickly, the amount of current that's in the circuit starts falling off and it's approaching zero. Eventually it's going to be basically arbitrarily close to zero if I give it enough time. So a couple of different things I have to tell you about this. First of all, what to start with? Let's write an equation for this one. So Q, as a function of time, the amount of charge that's on the capacitor, is equal to Q max, the maximum you could possibly put on there, times 1 minus e to the minus t over a constant tau, the Greek letter tau. Notice there's going to be some constant values in here. The maximum you can put on the capacitor Q is, as before, equal to C times V. This tau is a time constant that has a beautiful name. It is known as the RC time constant. And it is something that sort of tells you how quickly this particular capacitor can be filled up. And the equation is the name. This is one of those cases where it's just like beautifully put together. So tau is literally equal to RC. You gotta love that. So it's called the RC time constant, and RC is the equation for it. Now, if I just have one capacitor and one resistor, this is easy. If I have multiple capacitors or resistors in series or parallel, I have to find the equivalent resistance and the equivalent capacitance and put it into that equation. And then T is the only variable there. So I can use this equation, put the constants in there, and then say, okay, after 2 seconds, how much charge is on the capacitor? After 3, after 6, after 100 seconds, okay? It's a function of time. So this is the equation that we use for charging. We can also write a similar graph and say that the voltage across the capacitor as a function of time is equal to the maximum voltage it can ever be times this exact same thing. And it turns out you're basically going to get a curve that looks almost exactly the same if you're talking about the voltage on the capacitor. The shape looks the same, the values are of course different. So these functions essentially graph for you an increasing exponential function. It's something that represents a graph like that that starts off fast and then tails off towards some maximum value. The current, as we said, is that shape. It's a decreasing exponential. It starts at some value, rapidly falls off, and then begins to approach zero. We can write a function for this and say that the current through the circuit is equal to something that looks just slightly different, I max. And this time we leave off the 1 minus. So it's just e to the minus t over tau. So functions that look like this are increasing exponential, and a function that looks like this is a decreasing exponential. So if you can sort of remember the quantity and what it's doing while charging, which ones are getting bigger, which ones are dropping off and getting smaller, you can remember which equation you're supposed to use, the 1 minus version or just the one without the 1 minus. This describes putting charge onto the capacitor, okay? Now we can take that exact same capacitor and put it in a circuit of its own. Notice in this circuit, I have a capacitor and a resistor and a switch. There's no source of voltage. If the charge is going to move, all of that charge is coming from the capacitor until it runs out, until it has nothing left and it's back to just being two conductors that are near each other. So you'll notice we're going to do a similar sort of thing. They said at t less than 0, the switch is open, nothing is happening. And then at t equals 0, we're going to close the switch and charge is going to begin to flow. And you can see it leaves the positive side of the capacitor, goes around, it's trying to get to the other side to balance things out. But that current can't last forever. It's going to die. That sounds sad, okay? The capacitor is sort of like a short-lived source of voltage, a short-lived power supply. So in this particular case, we're going to start with the maximum amount of charge we're ever going to have on the capacitor, and we're going to run out. We're going to start with the maximum voltage, and we're going to run out. We're going to start with the maximum current, and we're going to run out. Question?
Like, where does it go? Like, if it just stays in that loop, does it get lost through like the resistance and like the heat wire or something? Like,
where does it? What's it?
Like the current itself.
The current. So if you imagine the current as just being positive charges, it's literally going to the other side of the capacitor just to balance out those negatives and make it neutral once again.
So but okay.
Yep, good. Okay, your question? Or it just got answered? Yeah?
No. So do we just always assume max capacitance?
You might be given something for like what charge we start with here, because it could be partially charged, and then you're working from the maximum that it ever was when you made the connection. So it starts with whatever it has. It can never go higher than that unless I connect it back to the battery again.
Right, so then would that just inherently become the max?
Yes.
Okay.
Whatever it starts with is the maximum for this discharging phase. Okay? So if I were to draw some graphs, actually I'm just going to draw one and it's going to have all the graphs. So whether it's the potential on the capacitor or the charge or the current, it starts as high as it's ever going to, and then it goes to 0 as a function of time. Which means that all of these are going to have the exact same equation. So we could say that the voltage on the capacitor is equal to, I hesitate to use the exact same term, let's say the starting voltage times e to the minus t over tau. And charge on the capacitor is going to be whatever you started with times e to the minus t over tau. And the current is going to be whatever you started with times e to the minus t over tau. So in this particular case, everything is a decreasing exponential because if you give it enough time, all the charge runs out and the current just dies. The circuit dies, all is dead, everything is lost. You have a question?
Yeah. So you said it becomes neutral because the capacitor becomes neutral, right? And then just the resistor works. That's why we lose current.
I wouldn't say it's why we lose current. As current flows through it, it has collisions, it can do work on whatever's in there at the time and maybe generate a little bit of heat or something along those lines. But it's just the fact that the charges, like charges, repel each other and attract, or the same charge, like charges repel each other, opposite charges attract, that they want to get back to the other side and neutralize everything. That's the reason the current stops flowing. I no longer have a repository of charge on one side that really wants to get to the other side. It's not because of the resistor, it's simply because the resistor just happens to be along the path to the other side where the charges want to be. Yeah. Oh, sorry, I'll come back.
So does the current just flow until the charge is evenly distributed throughout the wire?
Not evenly distributed throughout the wire, but you have equal positives and negatives on both sides of the capacitor. So if I zoom in on this, we start with a situation where, and how should we put this? Let's imagine that this is like more positives than negatives. Okay, there's still some negatives that's perhaps scattered in there, but it's more positive than negative. And this side is more negative than positive, even though there's maybe a few positives hanging out. Well, since I have too many positives here, positives are going to repel each other and start to run around and come to the other side and begin to fill this up. Once I have equal numbers of positives, negatives down that side, I'm also going to have equal numbers there. And now it's like, oh, we have no reason to go anywhere. There's no net repulsion, no net attraction. So it's not being spread through the wire. They're literally, they make a trip around and stop. And once that all balances out, everything's done. Does that answer or satisfy the
I
remainder
just
of your
want to know
question?
if the resistor has like an effect on it, like, or no. Or if we remove the resistor, will it still happen?
If you remove the resistor, the whole process is just going to happen faster. You could think of the resistor as something that sort of slows down the process, so it's not like the charge immediately balances out. Maybe I would like some current to occur for a period of time. The resistor just sort of spreads it out through time. Yeah.
So I don't know why, but looking at this, the only thing that comes to mind is the cell phone battery. So what we're essentially doing is pushing through current that would then run through a resistor until the point at which both of them are equally charged, and then when you plug it in, it would then force
Yeah.
it back. So you have this kind of like difference.
Yes. So capacitors are actually being looked at as replacements for things like batteries we recharge over and over and over again. At this point, we don't get as much out of it as we do with a traditional battery. The concept's the right idea though. Like we connect it to a power source, charge it up, and then it's temporary. At this point, having the extra chemistry and everything in there to keep the charges apart, that's something that can last longer. Capacitors are generally used in a circuit like this for something where you need a burst of charge just over a split second or at maximum maybe a few seconds. And that's as good as we get. But your concepts are kind of the same. If anybody remembers, and it feels like we talked about these things before. Yeah, the disposable cameras, yes, we talked about those in here. That's a case where you need some charge briefly just to flash the bulb, right? The flash on there. That's essentially what this is. It's a charging and discharging circuit. You hold the little button down, it goes, it makes a little noise. That's when we closed the switch and tried to put as much charge as we could on the capacitor. And then when you actually take the picture, it's closing the switch the other direction, taking a battery out of the loop and saying all the charge just runs out. It's quickly gone. Everything is lost. Nothing else is happening. Look into supercapacitors, if you want to look into that more and look at the research about using those as replacement for chargeable batteries. Okay, let's do an example with this. Let me show you how some of this comes together and works. And then we'll be just about done for this chapter, and I'm going to give you a problem to work, and we'll be done for the day. So let's see. Let's say we had a circuit that looks something like this. Let's switch colors. I'm going to put a resistor here. We'll call that R1. We're going to go over to here. We'll call that point A. What do we want to do here? Ignore some of these extra lines. My apologies. We're going to say this is a switch that can sort of go to two different points. So that might be a little different, but hopefully you can get the idea. This is R2. We've got a capacitor over here. And then we're going to have a resistor 3 there. And then our source of voltage. So that thing in the middle is a switch. It's just I can easily put it over to point A and do one thing, or I can put it over to point B and do another thing. It's a way of combining both charging and discharging circuits in one diagram. And on top of this, I'm going to give you some numbers. So the voltage is 50 volts. Resistor 1 is 10,200 ohms. Resistor 2 is 20,000. And resistor 3 is 1,300. The capacitance is 120 times 10 to the minus 6 farads, or 120 microfarads. And eventually you will have all that written down. Solve the problem.
Did you say 50 or 30 volts?
50. Follow the red dots. You're getting sleepy. Okay, so let me describe a couple of things about this circuit first of all. If I move this switch and make a connection over to point A, notice what I have. In that case, I'm connected to everything around the outer loop. But this resistor is not in play because there's no path, no closed path that goes through that resistor, okay? I will have a capacitor, 2 resistors, and a voltage source. So I'm going to be charging the capacitor. If instead I connect it over to B, well then this whole part with A and resistor 1 and the voltage source don't have a complete path. So they're essentially disconnected, not going to do anything. And then I just have this right loop where I have a capacitor and 2 resistors, okay? So A is considered charging, B is discharging, all right? So let's describe what we're going to do. We are going to start at time equals 0. We're going to move the switch to point A. This means we're going to be charging the capacitor. We'll say that it's initially uncharged. And we're going to leave it that way for a few seconds. Okay, so specifically, we're going to charge for 4.7 seconds. Maybe that's enough to completely fill the capacitor, maybe it's not. Okay. Then we are going to switch, for whatever reason I can't write the word switch, over to B. at which point we'll be discharging the capacitor from whatever state it reached during that first 4.7 seconds. And then we're going to discharge for 3 seconds. And at this point, I want to find a few things. I'd like to find the voltage across the capacitor and the charge on the capacitor at this point in time. We're going to charge for 4.7 seconds, discharge for 3, and then at that point, I'd like to see exactly how much voltage there is across the capacitor and how much charge remains across the capacitor. So first of all, let's solve for some time constants. I need the time constant when we're switched to A, and I need to find the time constant when we're switched to B. So this is just going to be R times C, and this one is going to be R times C, but I need to look specifically at what R's and C's are in the circuit at that point. So let's see, when I'm switched over to point A, we're just dealing with this outer loop. You'll notice that R1 and R2 are then in series with each other, so I can just add them. So that means when I'm switched to A, this is going to be R1 plus R2 times the capacitance. So that's 10,200 plus 20,000 times the capacitance, which is 120 times 10 to the minus 6. Both big and small numbers. You should get, after all of that, a nice number like 3.6. And the time constant is time, it's measured in seconds. That's not too bad, right? What resistors are in play when I switch over to B? Make this connection. If I'm switched here, I just have this part. So R2 and R3 are in series with each other. Okay, so we can go over here and write this as R2 plus R3. And I still just have that one capacitor. So let's see, R2 is 20,000, R3 is 1,300, and the capacitance is just like what it was before. So that comes out to be 2.6 seconds. So we're going to use both of those values in our equations coming up. So I can't find anything out about how much voltage and charge I have left over at this point unless I find how much I charged it up to begin with, okay? We don't know if it reaches the maximum values or not, so we're just going to have to find out. So let's start by finding the voltage across the capacitor at time equals 4.7 seconds. So for charging, we write this as Vmax times 1 minus e to the minus t over tau. And we're just going to plug all the numbers in and see what we get. What is the maximum voltage it can ever get in this circuit? We're connecting it to a battery that has a certain voltage. If I leave it there forever, what value is it going to get to? 50. It can't get any higher than the voltage I'm supplying to the circuit. So we can say that Vmax is going to be 50, and we'll multiply that by 1 minus e to the minus 4.7 over tau A, which is 3.6. You might want to try punching that in your calculator just to make sure that you can use the e function, the exponential function on your calculator. So you'll want to divide the negative 4.7 by the 3.6 and then hit the e to the x button to get that number. And if we all end up on the same page, you should get about 36.4 volts for VC at the end of our charging phase. Yeah,
Is that 3.6 under the 4.7 negative?
that is 3.6. Negative 4.7 divided by the 3.6 time constant we got up there. Okay.
That's the voltage across the capacitor.
That is the voltage across the capacitor at that point in time. The time change is making the light in here different. The light is getting low. Yeah.
Why do we have to be minus 1 minus dV versus negative?
That's the equation we use during charging. For any quantity that's like increasing towards some maximum, that's going to be the function that we use. Okay? So the maximum value is 50. We didn't leave it there long enough to charge all the way. As far as it made it was to 36.4. So if I were to go back and look at our charging graphs, it's almost like, I don't know, we got to like about here and said, enough charging, let's start discharging it. Okay, we didn't allow it to go all the way up. So let's see, we could, if we wanted to at this point, we don't need to define what we want to find, but just a little bit extra. At this point, we could say that the charge on the capacitor is equal to C times V. And this would be the charge at this point, not at any point, it's just how much charge it currently has. And it's going to be 120 times 10 to the minus 6 times this 36.4. You would find 0.0044 coulombs on the capacitor after 4.7 seconds of charging. So we sort of know where we stand when we start discharging, okay? That's as far as we allowed it to charge. Are you okay with the charging part? It's mostly understanding the circuit and then just using these equations. Just plug the numbers in and see what you get, okay? So once we switch over to discharging for 3 seconds, this is going to be my starting voltage for that part, and it's going to start to run out. So we're going to say VC at t equals 3 seconds is V start times e to the minus t over tau. Except now our time constant is when we've switched over to B, and our starting voltage is this, and we're not using 1 minus because this is a quantity that's falling off, it's not a quantity that's growing, okay? So if you plug your numbers in here, you're going to have 36.4 times e to the minus 3 over 2.6, which should give you 11.5 volts remaining on the capacitor after 3 seconds of discharging. And then you can once again use Q equals C times V, so that's 120 times 10 to the minus 6 times 11.5 volts, and it'll tell you exactly how much charge remains, which is 0.0014 coulombs remaining. Yes, you can do this, maybe. Review it, think about it. I think you can do it. Anybody? Any questions up there? Anything that's bothering you at all? Okay. For the remainder of the time,